Now it's time to talk about springs. Springs are a very interesting way to store energy. You've thought about your typical spring like a slinky or something. It's attached to the wall, and it has a coil-like design. The spring itself has a certain length L, but that's not what's important to the spring. What's important is if you were to compress the spring this way and shorten the length. So here was the original L, and now you're going to make the spring be significantly shorter. You've shortened it by a distance which we're going to call X. X is the amount of stretch or compression. Then the spring is going to respond, and if it is a classical spring, it is going to respond by obeying Hooke's law. Robert Hooke, I believe, was the guy's name. And he said that the force that a spring exerts is minus K times X. Minus because the spring always pushes in the opposite direction. If you move the end of the spring in the negative direction, it's going to push in the positive direction, and vice versa. K is a spring constant, which tells you how stiff or loose the spring is. Stiff means very hard to push and pushes back hard, and loose means very easy to push. Spring constant. And this, of course, is the amount of the stretch or compression. Now, since this is measured in newtons and X is measured in meters, it must be that the spring constant is measured in newtons per meter. That way the meters cancel and you get everything right. Newtons per meter, in other words, how much force for each meter of compression or stretch that you're going to get. So that makes perfect sense. So if this is and we can ignore the minus sign because that's just a directional thing. And remember that energy is a scalar. So we're just generally looking at absolute values of things. So now we have a situation where the force is, so this is going to be L, the length of the spring right here. And the force is going to be negative here and positive here. This is the force, and K is the slope of this line, with this being the stretch. Well, we just got done talking about how you can find the work done in stretching a spring by looking at the area under the curve. So if we were to take the spring and stretch it, let's pull it out, and we were to pull it out here to a position L prime, why then we would need to find the area under this part of the curve. But that's just a triangle. So the area under that part of the curve is fairly simple. It's going to be 1/2 of the maximum force times the distance we stretched it, which of course is L prime. Or we could just call it X again. In fact, I do just want to call it X again. So 1/2 Fx. Oh, hold on a second. But F itself has X in it. So this is 1/2 of Kx times X again. This is 1/2 Kx squared. So the work done in stretching a spring is 1/2 Kx squared. And that comes from just figuring out that the Hooke's law gives us a linear relationship between force and displacement of the spring. Yeah, thank God I changed from L prime back to X, because both of these things would be L prime, and then it would be the L prime squared. But L prime is just X, how far you stretched it. So we already had a variable for that. So I made a small mistake. If I was going to do this video again, I would fix that. But I'll do that next year, or next time we have a giant, tremendous lockdown and I have to teach at a distance. So this is the formula for the work done by a spring. Now I'm going to tell you something that's coming, and that is that the work done by a spring, work done on a spring or by a spring, actually is equal to its potential energy. Once we have stretched that spring out, it has something, it has energy in it that we could get back. Well, the easiest way to get it back is just let go of the spring. It'll come shooting back. And in fact, a lot of toy guns use a spring to compress some air and shoot a ping pong or a marshmallow out of the end or something like that. Or even those plastic darts, which, oh, the Nerf darts. Oh my God. The new Nerf darts and the new Nerf balls, those guns are so great. I'm going to have to get some. Okay, So that's about it for work and energy. The rest of the time will be spent doing examples, and look forward to those.